If you build enterprise-level 3D applications, you already know the bottleneck. Managing massive digital twins or industrial simulations means forcing huge amounts of geometric data through a pipeline that simply wasn't built to hold up under the pressure. The core friction comes from how modern development cycles actually operate. Teams typically author their 3D asset in one specific application, like Maya or Blender, but they deploy the final interactive experience in a completely different environment, like Unreal or Unity. To bridge these isolated software islands, engineers default to legacy exchange format, specifically FBX or GLTF. But pushing complex industrial scenes through these specific formats forces a destructive translation. The data is baked down, compressed, and restructured just to satisfy the export parameters. The first immediate symptom of this process is the persistent scale mismatch. A factory modeled accurately in millimeters frequently imports into a game engine completely out of proportion. Next comes the total loss of material data and the flattening of complex scene hierarchies. Node networks break down and component trees collapse into rigid, unusable static meshes. Pushing highly detailed digital twins through these linear destructive handoffs guaranteed technical depth, making it nearly impossible to scale up large enterprise interactive systems. This exact interoperability failure is the problem NVIDIA's Omniverse platform was built to solve. Yet, there is a persistent industry misconception about what this platform actually is. Many experienced developers mistakenly view Omniverse as another monolithic creation editor, something designed to compete directly against Unreal Engine or Blender. NVIDIA's early packaging actively fueled this misunderstanding. The heavy focus on the now depreciated Omniverse launcher and the Create desktop applications made it look like a closed suite you had to migrate your entire workflow into. The technical reality is much more useful. Omniverse is designed to sit directly between and above your existing tools as a non-destructive interoperability layer. It operates on a disaggregated architecture. Instead of focusing your pipeline into a single massive application, it acts as the lightweight connective tissue holding your diverse toolkit together. This framework purposefully extracts heavy computational tasks like path traced rendering and multi-physics simulation entirely out of the traditional monolithic editor environment. Moving from a front-end editor mindset towards this back-end pipeline framework allows for a distributed 3D architecture where each tool in the styling focuses strictly on its specific core function. The foundation of this architectural shift is OpenUSD or Universal Scene Description. You cannot treat USD as a static file format like an OBJ. It is a highly relational scene description framework. Instead of merging geometry, USD relies on referencing. Editing a subassembly in one file instantly updates the master scene without breaking the project's structural integrity. It manages massive asset options natively through variants, allowing developers to store multiple configurations like different materials or mechanical components within the exact same scene hierarchy. Because this structure is non-destructive and relational, it completely bypasses the material loss and hierarchy destruction that plague legacy FBX exports. To manage this data structure across a massive team, NVIDIA provides Omniverse Nucleus. Nucleus serves as a real-time routing engine and database, synchronizing these complex USD layers across the network as developers work. This exact setup enables true live sync capabilities. A modeling adjustment made in Blender is instantly reflected inside a Unity or Unreal environment because both engines read the exact same underlying USD data. By utilizing OpenUSD and Nucleus, developers eliminate linear asset handoffs entirely, establishing a centralized living source of truth for the entire pipeline. Now that the data structure is solved, we have to look at how heavy compute operations are actually executed. Historically, running a complex background simulation meant loading a 20 GB game engine editor interface just to assess its physical calculation. Omniverse addresses this through the complete unbundling of the game engine into modular standalone libraries. The first independent module is the OVRTX library. OVRTX is a decoupled path tracing renderer. Instead of opening a massive 3D application to view a scene, a developer can execute photorealistic rendering natively using a simple pip installable Python script. The second major module is the OV Physics library. This module handles rigid body dynamics, cloth simulation, and complex tensor bindings completely asynchronously. The most critical advantage of these specific libraries is the ability to execute headlessly. Stripping away the visual UI bottleneck means that backend robotic training or multi-physics simulations process exponentially faster than real-time, outputting the mathematical results without waiting on frames to render. Decoupling the physics and rendering algorithms from visual editors allow engineers to bypass interface overhead and maximize raw GPU compute efficiency from massive enterprise workloads. The immediate friction point in adapting this pipeline is the learning curve. Manually authoring the incredibly complex raw USD syntax required to build these relational scenes is tedious. NVIDIA addresses this barrier directly with pre-packaged skills markdown files. These specific context files ship natively alongside the modular Omniverse libraries, formatted precisely for artificial intelligence. The workflow is highly efficient. You point a local AI coding agent like Cursor specifically at this skills directory. The AI uses this detailed context to instantly write the required scene relationships like render products or doom lights directly into your script, bypassing hours of manual troubleshooting. Integrating these AI skills shifts pipeline engineering from a tedious exercise in syntax debugging into high-level systems architecture. To see how these disaggregated components function together, we can look at a concrete, real-world enterprise deployment. The goal is to deliver a fully interactive, path-traced civil engineering training application that runs natively inside a standard web browser. Tracing the pipeline backward, we start at the content creation layer. The core foundation models and construction props are authored in Blender, then synced non-destructively as USD layers. From there, we move to the central processing layer where raw logic is executed. Inside that server, the OV physics module handles the complex structural collision data and crane movement simulations quietly in the background. Concurrently, the OV RTX module reads that exact same USD data to calculate physically accurate path traced lighting across the entire construction site. all of this heavy compute is processing locally on a back-end RTX cluster, completely offloading the hardware burden from the end user. The final bridge that makes this enterprise ready is the deployment streaming layer. The Omniverse Web SDK utilizes WebRTC protocols to pipe the final visual output directly to a thin client framework like Three.js or React. This is the operational victory. An end user can interact with a massive, complex digital twin on a lightweight device without ever installing monolithic software or requiring a discrete GPU. Treating Omniverse as a modular OpenUSD based backend achieves a specific technical trifecta: cinematic render fidelity, precise multi-physics mathematical accuracy, and real-time collaborative pipeline management with almost zero defect or zero tolerance. This is the future of industrial and product design.